In this section, I'm going to be talking about standardization and normalization. Before I do, according to Wikipedia, feature scaling is a method used to normalize the range of independent variables or features of data in data processing. It is also known as data normalization and is generally performed during the data processing step. Now, if you recall in CRISP DM, CRISP, which is the cross-industry process for data mining, the data pre-processing step comes right after data understanding. So it starts with business understanding, data understanding, and then data preparation, and then of course, modeling, evaluation, and deployment. Now in feature scaling, you are attempting to rescale the data values, and we're going to be talking about two different methods, standardization and normalization. In standardization, you are attempting to bring a feature's values to a small range centered near by computing observation minus mean divided by standard deviation. Observation minus the mean divided by the standard deviation. That computes a score called z-score, which is a number of standard deviations from the mean value in the reference population. And if you haven't seen this before, this is a normal distribution. And as you can see here, the z-score, when the z-score is 1, then that means it is one standard deviation right over here above the mean. A z-score of 2 means it's 2 standard deviations above the mean. And of course, a negative 1 or a negative 2 z-score means it's either 1 or 2 standard deviations below the mean. And of course, a z-score of 0 tells you the value is exactly average. Now, if you look at the z-score of 2, it shows 97.7%, which means that that 97.7% of the population scores lie below that particular score. And 2.3% of the scores lie above that score. And as you can see here, 95% of the values is about 1.96 sigma, and 99% of the values is about 2.58 sigma. One would ask, well, why standardize? Well, a lot of times, as you notice, the range of values of raw data typically varies quite a bit. And especially when it comes to machine learning algorithms, the objective functions that you are creating will now work properly without normalization. One example, if you have a classifier that's calculating the distance between 2 points, you're using the Euclidean distance. And if one of those features has a broad range of values, the distance will be dominated by that feature. So it's best if all features are normalized so that each feature contributes approximately proportionally to the final distance. Let's attempt to perform feature scaling via the two methods, standardization and normalization. So I'm going to download a data set from Kaggle. And this data set is about food choices, where college students' food and cooking preferences are collected. And again, this data set includes information on food choices, nutrition, preferences, childhood favorites, and other information from college students. It mentions over here the inspiration. How important is nutrition's information for today's college kids? Is their taste in food defined by their food preferences when they were children? So it's a fun data set, and it's collected from students from Mercyhurst University. And the survey, as you can see here, contained the following questions: GPA, gender, breakfast, calories, chicken, guessing the calories in chicken, calories per day, calorie scone. So in this case, they're guessing the calories in a scone from Starbucks. Comfort food, lists the 3 to 5 comfort foods that come into mind. The reasons, the comfort food reasons coded. In this case, if it's stress or boredom or depression, hunger, laziness, cold weather, watching TV. So it's a fun survey. that we're going to get to play with. So going back to our notebook, first thing I'm going to do is load my dataset, whereby I import the libraries and load my dataset into food choices data frame. I'm going to take a quick look at what my data frame is going to look like. And as you can see here, you have GPA, gender, breakfast, calories chicken, and the other features that we just talked about. As you can see here, these three dots indicates that there are some other columns that are there that are not displayed. So in order to display them, I can just type pd.set option display max columns. And now we can see all the columns in my data frame. Excellent. Now on the flip side of that argument is that if I want to list all my rows, as you can see here, there's some rows missing. So I can type pd.setOption display.max_rows. And now you can see all the rows listed. Now also, if you notice here, I have some values that are missing or have a string typed into the value when it's supposed to be a numeric value. So we're going to have to clean that up in pandas when it comes to the GPA. And I'm going to be actually looking at another feature here, which is the weight. I'm not answering this, or not sure. So I'm going to type the following. Food choices. And I'm going to first clean up my weight. Pandas to numeric. Food choices. Weight. And of course, with errors, I'm going to coerce. Which essentially means that if there are any errors that are encountered, then any invalid parsing will just be set to a null value. You can actually control this by changing it to raise or ignore. And again, the pd.numeric is you're converting the argument to a numeric type. So to simplify, I want to do this for weight and GPA. Because when we're going to try to standardize or normalize, if it's a string, i.e. when the value is a string, then we're going to run into some issues. All right. So the next cleanup that I would like to perform here is my comfort food reasons coded. I want to take a look at the column. But on the flip side, if we look at our Word documents, comfort food reasons coded, instead of value, I want to add a column that would reflect what it means. So 1 is stress, 2 is boredom, 3 is depression, 9 is watching TV, and of course 9 is none. All right, so how do you do this? Well, I am going to create a dictionary. But before I do, I want to also talk about gender. 2 and 1, I want to change that also, whereby or add a column when a value is 2, it means it's a male, and 1, it's a female. So I'm going to copy and paste some code. I created a dictionary, which is identical to this, whereby 1 is stress, 2 is boredom, all the way to 9. And also over here, gender convert, male, female, 1 is female, 2 is male. I'm going to use a lambda function to get the associated string with comfort food reasons coded and my gender, and create a column called comfort food reason and another column called gender. So let's do that. And as you can see here, 2 gender, and over here, that means it's the male. Awesome. And over here, 1, 1, 1, 1. So the rest should be females. Female, 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 female. Excellent. And over here, just a quick check. You have a none and a stress. Over here, you have a value of 9 and 1. And if we just wanted to do a quick check, 9 is none and 1 is stress. All right. We are in business. Now, what I'd like to do is, again, copy and paste some code. I would like to create a box plot and look at the comfort reasons versus weight. And my hue is going to be gender. And again, with hue, essentially what we're doing is we're grouping variables that would produce points with different colors, in this case, male and female. Now, this gives us a little bit of insight when it comes to those college students that were surveyed, comfort food reason, and their associated weight. So the males that are eating out of boredom or stress or happiness tend to be on the higher side versus the ones that are over here experiencing depression, sadness, or stress. So again, this is just a data set that I use from Kaggle. Of course, this doesn't apply to the entire population of students. This is, again, I'm just playing with the data that I have available to me. Now again, for fun, if I wanted to create a scatterplot matrix, then I'm going to copy and paste some code. Going to look at my weight and my GPA as my variables. And again, my hue is going to be gender. And again, you can see over here a layered kernel density estimate with semantic mapping. So at least now we can visualize the distribution of observations in our dataset when it comes to weight and GPA, and can interpret them accordingly. Awesome. So the next part, I'm going to be using my function, my scale function. So therefore, I'm going to need to import my pre-processing library from sklearn in order to standardize the data frame and output an array. So I'm going to go ahead and copy and paste some code, whereby I'm going to import the necessary libraries, standardize the data, weight, and GPA, and then output my standardized data as a data frame. I'm going to also include my gender column. And last but not least, just for fun, I'm going to create a line plot of weight versus index, just to see what it's going to look like. And as you can see here, it's a little messy, hard to understand, but at the same time, you can see that the weight has now been standardized from -2 to about 3 point something, 3.5. So this again is your z-score based off of the standardized data. Now, since this is a little bit confusing, I'm going to go ahead and create a KDE plot to visualize the distribution of observations in my dataset. We're going to go ahead and run. Excellent. So as you can see here, this KDE, it represents the data using a continuous probability density curve in a couple of dimensions. And as you can see here at the bottom, my values are now standardized when it comes to the weight. much cleaner than this. And of course, verified, of course, when compared to my scatterplot matrix here, where my range was from about 100 to about 300 pounds. Now it's between a z-score range from -3 to about 4 or so. Of course, there is always another method of creating a KDE plot. I'm going to go ahead and copy and paste, layered on top of, in this case, a histogram. So I'm going to create a KDE plot and a histogram. And my X is going to be my standardized weight. Voila. So again, this is the same plot, but I have now my histogram layered with my KDE plot. Fantastic. So let's talk about the other scaling method, which is called normalization, aka min-max normalization. It's rescaling a feature's values to the range by computing observation minus the minimum divided by maximum minus the minimum. So we're going to be using the min-max scaler, which is part of the pre-processing library of sklearn, to normalize the data frame and output an array. So I'm going to go ahead and copy and paste some code, whereby first I'm going to normalize my data, create a data frame, add another column to my data frame called gender, and last part is to create a line plot. And as you can see, this line plot is a little confusing, but my weight values have been normalized from 0 to 1. Outstanding. Now for fun, let's create a distribution plot. I'm gonna copy and paste some code here. Gonna take a look at my weight, create a KDE plot, rug equals true. And as you can see over here, I was able to create a plot resulting from a bivariate distribution. And this is my rug over here, which essentially draws ticks along the x and y axis, complementing my KDE plot, but at the same token, not as obtrusive as my histogram layered on my KDE plot. Talking about that, now I'm going to go ahead and copy and paste some code to layer my histogram onto my KDE plot. And as you can see here, my values have been normalized between 0 and 1. And of course, the last part over here, I'm going to create a distribution plot, namely a KDE plot with a rug enabled. Outstanding. So just to conclude, we were able to apply feature scaling and use the common feature methods, standardization and normalization. We were able to normalize our weight from a range of 0 to 1 via our min-max scaler from the pre-processing library of sklearn. Also, we were able to standardize our data from our scale function that is in our pre-processing library of sklearn to standardize our data frame and output standardized data with z-scores that range from -2.5 sigma to about 4 sigma or so, which is standard deviations from the mean, telling you where the score lies on a normal distribution curve. Outstanding. This concludes our section on standardization and normalization.